In this section, we're going to talk about lines. Now, as simple as lines can be, they actually turn out to be very important for calculus. In fact, a lot of what we're going to be doing later on is trying to use lines to talk about other particular graphs and what we can call functions. Now, in general, the equation of a line looks something like ax plus by equals c. Every line can be given an equation like this, and every equation like this corresponds to a line as long as not both a and b are equal to 0. But it is actually more common to use different forms for the equation of a line, such as slope-intercept form or point-slope form. But in order to talk about those, we're going to have to first talk about slope. So what is slope? Well, if we have a particular line, let me go ahead and just draw a line in here. And we have 2 points on that line. Let's say we have a point here that's x1, y1, and a point here that's x2, y2. We can actually compute the difference between our x values and the difference between our y values. These are frequently referred to as the rise and the run. So if we actually complete a triangle, the difference in our x values will be the length down here on the base, and the rise, the difference in our y values, is the length of the side over here. If we write those out, you can say that the run, we frequently also write differences using this delta. Delta here just means difference, or stands for difference. And it's just x2 minus x1. The rise, write that as delta y. That's y2 minus y1. Now, technically here we could swap the order of do x1 minus x2 and y1 minus y2. We do want to be careful and use the same order for both of these for what we're going to do with it, though. Because the slope, usually written with the letter m, it's kind of just a standard notation there. It's going to be the difference in y's over the difference in x's. Or we could also say the rise over the run. And if we write that out, we just have the difference in our y's divided by the difference in our x's. Now, of course, there is a possible problem here in that if we have our 2 points having the same x value, we're going to get a 0 on the bottom, and so our slope formula is going to break. This happens exactly when we're dealing with a vertical line. So we're going to just say that a vertical line does not have a slope. And we'll come back to those a little bit later. That's why we need to exclude those from whenever we talk about things like the slope-intercept form or the point-slope form. Let's do a couple of examples of finding slopes for some lines. Specifically, I'm going to work on problem 31. So this problem from the book gives us 2 points. It gives us 4, negative 1, and 2, 7. We're going to need to find the difference between our x values and the difference between our y values. But before we do that, I want to make sure we're clear that unlike what we did with the distance formula a couple sections ago, we do need to be careful about which order we do the subtraction is. Basically, we need to use the same order on top and bottom, or we're going to get the wrong answer. We're going to get a negative instead of a positive, or a positive instead of a negative. But the slope here, we have our difference between our y's. So I'm going to go ahead and pick the 7 first. So 7 minus the negative 1. Since I picked the 7 first, now I need to pick the 2 first. I don't have a choice at this point. And now we have 2 minus 4. So our top here is an 8. The bottom is a negative 2. So we get negative 4 overall. Let's do problem 36. This time we have the points 3, negative 13. and -2, -3. We do the same process. This time, I'm going to go ahead and pick the -13 first, and I'll subtract the -3 from it. So the difference between our y's. Then now we have to pick the 3 first, and subtract the -2 from it. Be careful here, this is not 1. The bottom here is actually a 5. The top here, -13 plus 3 is going to be a -10. And so overall we get a -2. Those are the slopes of these lines. And we'll come back to actually finishing the problem, finding the full equation of those lines in a moment. So once we know the slope of a line, we're in a very good position to find its equation. Generally, we need two pieces of information, but most of the time it's usually the slope, or at least we find the slope using whatever information we're given, and a point that's on the line. So if we have a slope of m, and a point that's on the line, so let's say x1, y1. There we go. Recall that if any other point is on this line, if x, y is on that line, then this point along with the point that we're given have to give us this same slope. That means that our slope formula, m, is equal to our difference in x's, do x minus x1, divided by a difference in y, sorry. Y is on top, difference in y, so y minus y1, divided by a difference in x's, x minus x1. I'm going to go ahead and just multiply the denominator over on both sides. That will give us that y minus y1 needs to equal m times x minus x1. This is actually a nice simple equation for our line already. We refer to this as the point-slope form. And it's generally the way we would actually start with information and get the equation of a line. Now in general, actually let's go ahead and box this before I move on. Just to be clear, this is an important thing you're going to want to remember. But we do want to take it a step further and kind of solve for y. Just move the y1 over to the other side, and we'll go ahead and expand by distributing the m to both terms here. So here we have our variable y, we have m times our other variable x, but everything over here are just numbers. And in a particular example, we would have everything there we just combine into one number. So I'm just going to call this a b. So that we have y is equal to mx plus b. Now this b is actually kind of special. If we plug in 0 for x, we just get that y is equal to b. And therefore, 0b is the y-intercept. That's where this line hits the y-axis. And for that reason, we refer to this form here as the slope-intercept form. Generally, if we're just given information about a line and we're trying to find its equation, we'll generally have to use the point-slope form to find that, because usually we're not given enough information to immediately know what that intercept is. If we're given the intercept, then that's great. We can go straight to the slope-intercept form. But usually we'll have to go through the point-slope form and then do some solving to put it into this form, because this is the easiest form to actually work with. It's not only are the m and the b unique to that line, every line will have a unique m and b as long as it's not a vertical line. That's not true up here. We can have different points that we plug in, and the equations will look different, But yeah, so the equations will look different, but they're all still equations of the same line. But when we get to the slope-intercept form, there's only one equation that's going to be valid for that given line. It's just that most of the time we can't get to this immediately. So let's go ahead and put that into practice and find the equations of these two lines. Now, again, we are going to use the point-slope form first, but we're going to put our final answers in slope-intercept form. And it doesn't really matter which point we choose. So for this first one, I'm just going to pick the first point, just because it's the first one. So we have 4, -1 is my point. My slope is -4. So I have y minus my y value of -1 is equal to my slope, -4, times x minus my x value of 4. So technically we already have an equation for the line. I'm going to go ahead and distribute the -4, and I'm going to move the -1 to the other side. So now y is equal to -4x. -4 times -4 is a plus 16. But now I'm adding a -1 to that side. So my final answer here, once I combine the 16 and the -1, is y is equal to -4x plus 15. Here, again, it doesn't matter which point we choose. Since the first one has a 13 in it, I'll go ahead and pick the second point just because it has smaller numbers. But we'll get the same answer either way. So I take y minus my y value, so minus -3, is equal to my slope, which is -2, times x minus my x value, which is -2. Again, we're going to distribute the -2, so we have a -2x. We have a -2 times a -2. Well, 3 negatives makes 1 negative overall. So we're going to have a negative 2 times 2, which is 4. But I need to go ahead and add a -3 over to this side. So our final answer this time, we have y is equal to -2x. And then the -4 and the -3 combine to give us a -7. Now, one thing that we can do in both of these situations is test our other point. So we used 4, -1 in order to come up with this equation. We need to make sure it also works for 2, 7. That's an easy way to check to make sure that it's correct. If I plug in 2 over here, we have -4 times 2 is -8. If I add 15 to that, I get 7. And that's exactly what I wanted to get. So this particular equation, it's the equation of a line, and it definitely does contain both those 2 points. So it is the correct equation. Same thing down here. If I pick my 3, because 3, -13 is the point that I didn't use. So I put 3 in here, I get -2 times 3, which is -6. -6 times -6 plus 7, -7, or -6 minus 7, does give me a -13. So this one is correct as well. Now let's see how we would graph a particular line if we're given its equation but we don't know the points on it yet. So let's actually work out some problems here. Let's do problem 21. In this problem we have 3x plus 2y is equal to 4. And we want to graph this line. Graphing a line really just comes down to finding 2 points that are on that line. And then we'll just draw a straight line through those 2 points. 2 points is enough to determine a line. But what are some easy points? We could just try plugging in some numbers and seeing what we get. Or we can actually go about this a little bit more algorithmically, I guess. Basically, we'll first put this into slope-intercept form. So I'm going to solve for y. Just basically put everything that's not a y over to the other side. So I'm going to, I saw the 2y for the moment. I'm going to move the 3x over to the side. I'll go ahead and put that in front. So if you want, you could put it at the back. So Sometimes it's nice to put the things that are negative at the back of the sums, like we have here. Now we need to divide by 2. So we have y is equal to negative 3 halves x, then plus 2. We have to divide both of those by 2. So this is our line in slope-intercept form. We know our slope here is negative 3 halves. Our y-intercept is 2, or really more specifically the point 0, 2. Let's write that all down. And once I have that information, I can then use it to actually graph my line. So I'll use my y-intercept as my starting point. So I'll just say here, let's say this is at 2, the point 0, 2. We know our line has to go through that point. If we use our slope now, we can actually determine another point. Recall the slope here is rise over run. We can pick any rise and run that we want as long as they are in this correct proportion. And since our slope is already given as a fraction, I'm just going to take the top of that fraction. I'm going to keep the negative with it, so a negative 3 for my rise. And then I'll pick the bottom, the 2, for my run. Remember, run is the difference in x's, so I'm moving over 2 to the right on my x's. And then the negative 3, that means I'm going to be moving down by 3 in my y's. In other words, we're going to go from 0, 2. I'm going to add 2 to my 0, and I'm going to subtract 3 add 2 to my x and subtract 3 from my y. And I'm going to get the new point of 2, negative 1. So we moved over 2 and down 3. And now we got this new point over here of 2, negative 1. And then once we have those 2 points, we just try to draw a line through them. Kind of missed there a little bit, but that's okay. You could use a straight edge if you're doing this by hand. I don't really have that option on my computer screen. But the point here is we now have a plot for our line. Let's do another one. Let's do problem 24. This time our equation is x plus 2y plus 10 is equal to 0. Again, we do want to get the slope-intercept form in order to graph this line. So I'm going to move everything except for the y over to the other side. So we have 2y is equal to negative x minus 10. Then I need to divide by 2. So we have y is equal to negative 1/2 x minus 5. Our slope here is negative 1/2. Our b is negative 5, so our y-intercept is 0, negative 5. Again, we can take negative 1 for our rise and 2 for our run. That means I'm going to add 2 to my 0. And I'm going to basically add a negative 1 or subtract 1 from my negative 5. So I get a negative 6. I go ahead and plot those 2 points. Since my y values are pretty negative, I'm going to go ahead and put my x-axis higher up. So we have, say, 0, negative 5, and then 2, I'm going over 2 and down 1, get 2, negative 6. And we get our line through those 2 points. Now, technically, there are other ways of approaching this. This is just one easy way to do it. Once we put it in the slope-intercept form, we basically already have all the information we need to just go ahead and draw it out. Now, I already mentioned that vertical lines do not have a slope, but that does not mean that there are no equations for vertical lines. The main important thing for a vertical line, If we go ahead and draw one of those out, so we have a vertical line here. The main characteristic thing of these is that every point on that vertical line has the same x value. In fact, they're all kind of determined by where that vertical line hits the x-axis. So what we can do here is say that whatever that common x value is, let's call it a, the equation of that line is going to look like x equals a. Since there's no y's here, y is allowed to be whatever we want it to be, and that gives every point on that vertical line. We can do a similar thing with horizontal lines. So I'll go ahead and draw a picture for this one as well. So we have a horizontal line like this. Every point on this line has the same y value. They're determined by where that horizontal line hits the y-axis. We'll call that b. We can basically say the equation of this one is y equals b. And if we compare this to our slope-intercept form of y equals mx plus b, we note that basically m has to be 0 in this particular case. So every horizontal line has a slope of 0. And the b here that we have, that I chose for this, is just the same as the y-intercept b that we had from before. We don't have a b for the vertical lines because we actually cannot hit the y-axis. There is no y-intercept for a vertical line. At least as long as the vertical line isn't the y-axis itself, in which case there's infinitely many y-intercepts. But kind of broke the idea in that case. Now the book actually does talk a little bit about parallel lines and perpendicular lines and how the slopes are related to those. If you are interested in that, you can go ahead and read through it. But we're not really going to be making a lot of use of that in calculus, so I'm going to go ahead and skip that for now. If we need it, we can come back to it and talk about it a little more then, but it's not really the most important topic for us right now. What is a little bit more important to us is kind of getting an idea of how slopes, what those mean in applications. So let's actually work one of our word problems. So this section actually has quite a few word problems to work on. I'm going to go ahead and do problem 87. In 87, this is a question about population. Says that the resident population of Wisconsin in thousands was 5,655. So remember this is in thousands. So really it's saying 5,655,000. But we're just going to write 5,655. This was in 2009. And 5,743 in 2013. Assume that the relationship between the population y, so they're going to be calling the population y, but they are doing it in thousands, so y is the population in thousands. So assume that the relationship between the population y and the year t is linear. So we're using t instead of x in this example. But they're also saying to let t equals 0 represent 2000. So instead of using 2009, 2013, we're going to use 9 and 13 for our t values. Just to make it a little easier for ourselves. So we're kind of not using the direct numbers. We're changing the units to thousands here. We're moving the 0 to make sure these are smaller, but it helps us out quite a bit. This problem has multiple parts. Part A, write a linear model for the data. What is the slope and what does it tell you about the population? So basically, we want to approximate the population over time using a line. And we want to find out what the equation of that line actually is. So first we're going to find our slope. Remember here, These are our y values, these are our t values, which are playing the role of our x values. So we're going to find our slope as difference in our y values. I'm going to go ahead and pick the bigger one first. And that means I have to pick the 13 first here. The difference in our on the top is 88. The difference on the bottom is 4. And so our slope is 22. What does this 22 actually mean? Well, one of the things that we like to do in math is kind of ignore the units until the end. If you're taking a science class, they kind of throw a fit about that. But it does help to actually identify what is going on. Remember, on top, the units here are thousands of people. On the bottom, we're talking about years. So what we're basically saying here is that this is 22,000 people per year. Essentially, the population is changing by 22,000 people per year, at least on average. The population of Wisconsin increased by 22,000 every year. This is what we refer to as a rate of change. Or more specifically, an average rate of change. We'll talk about other rates of change later on when we get to the derivative, but the main thing to note here is the connection with slope. Basically, slopes in applications represent rates of change, at least whenever we're dealing with instead of x, we're using t here for time. Whenever we're dealing with time, things changing over time, slopes basically become rates of change. Or slopes represent rates of change. That's the main idea that we want to have there. Now that we have the slope, we can actually go ahead and find the equation of our line. Recall that we're using these as our points. I'll go ahead and use the first one here. So we have y minus our y value of 5655 is equal to our slope of 22 times, now we're not using x, we're using t minus 9. We're going to go ahead and put this into our slope-intercept form. That means I'll go ahead and move the 5655 over to the other side. I'm going to distribute the 22 to both terms. We get a 22t, and then 22 times negative 9, but then added to 5655. You can go ahead and use a calculator to find that if you want. It turns out to be 5,457. This is our model, or specifically it's a linear model for the population. And what we want to basically say here is whether or not this really does actually agree with information about the population. And so that's what part B is asking us to do. Use the model to estimate the population in 2011. Now note here that because we did change 2000 to be 0, 2011 is going to be t equals 11. So our y in year 2011, we just basically plug in 11 for our t. We have 22 times 11 plus 5,457. You can go ahead and use a calculator to find this if you want. Get 5,699. Now in part C, they're asking us, it says, use your school's library, the internet, or some other reference source to find the actual population in 2011. How close was your estimate? So I basically went ahead and just did a Google search for the population of Wisconsin in 2011. Pretty simple thing to do there. We get 5.705 million people. Now keep in mind that since we were working with our y in thousands, this is really just 5,705,000 people. So our actual result And we're not really they're not really the same number. We're off by about 6,000 people. So our model, our linear model, is not quite correct. The population did not follow a line, but it was a decent enough approximation. We're not that far off. I mean, we were talking about 22,000 people changing every year, but we were only off by 6,000 people. So it is a decent enough approximation. In part D, they're asking, do you think your model could be used to predict the population in 2018? Well, keep in mind this book was published in 2017, so they didn't actually know what the population was going to be. But since we're in the future compared to this book, we can actually look that up. But let's see what our model predicts. In 2018, of course, remember that means our t here is going to be 18. So you have 22 times 18 plus 5,457. Again, go ahead and use a calculator here. This is 5,853. And if we go ahead and compare to a Google search, they say that the population of Wisconsin in 2018 was 5,807,000 people. We have to change those units. So I'll go ahead and write that down. And note, this time we're actually a lot further off. We're actually off by, we actually overshot by 46,000 people. And so what you can kind of note here is that if we're trying to use a linear model to extrapolate, we can end up off if we don't really have a linear model. So while linear models can be very useful tools and the easiest tools to be able to work with, we have to take some predictions from them with a grain of salt. But of course, maybe it would have been better if we knew this additional information about 2011. We might have used that along with one of these 2 points up here and maybe gotten a better estimate. Unless we were work that out ourselves, we might not know. But the point here is that this is a simple way of actually generating a prediction that may or may not be accurate, depending on whether or not our actual situation is linear or not. In fact, we're going to come back to this idea later on in situations that we know are not going to be linear. But we'll use the fact that lines are so easy to work with to actually get close enough approximations for what we need them to be. And we'll get more into exactly when we're actually going to be close enough and all that kind of stuff. But I'm going to go ahead and leave that here. So there's more word problems if you want to take a shot at those. In the next section, we'll go ahead and start talking about functions. The other main thing, along with lines, that are very important for calculus. So I'll see you in that video.